Tonight could be the night everything changes. 3I-ATLAS, the visitor from another star, is skimming past the Sun in what scientists call the acid test. If it accelerates or shows power beyond gravity's pull, then something, or someone, is controlling it. That would mean our first proof of alien technology. If it's natural, the mystery continues, but if it isn't, the universe just got a lot smaller. Stay with me as we analyse all the possible scenarios with their repercussions. Because by the time this night is over, everything we thought we understood about life, time and humanity itself could be rewritten. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and your thoughts on what might just happen tonight. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The one-line claim and perihelion reality check. If 3I-ATLAS does this tonight, nothing will ever be the same. Right now, as you listen to these words, an object from beyond our solar system is reaching the closest point in its journey around our Sun. We call this moment perihelion, and for this particular visitor, it represents something far more significant than just another astronomical milestone. This could be the moment when humanity discovers we are not alone in the universe, or it could be the moment when we confirm that the cosmos remains as silent and indifferent as we've always feared. Either way, what happens in the next 72 to 240 hours will reshape everything we thought we knew about our place in the cosmic order. The object in question bears the designation C/2025N1, discovered on July 1st, 2025 by the Atlas Survey Telescope in Chile. Scientists have confirmed it as the third interstellar visitor we've ever detected, earning it the informal name 3I-ATLAS. Unlike comets born in our solar system, this object came from somewhere else entirely, carrying with it the frozen chemistry and perhaps the secrets of another star system. Its trajectory tells us everything we need to know about its origins. The orbit is hyperbolic, meaning it will never return, moving through our neighbourhood at speeds that betray its extrasolar heritage. The excess velocity measures around 60 kilometers per second, far too fast for anything gravitationally bound to our Sun. Tonight, October 29th, 2025, 3I-ATLAS reaches perihelion at a distance of approximately 1.35 to 1.4 astronomical units from the Sun. That translates to roughly 203 to 210 million kilometers, placing it somewhere between Earth's orbit and Mars. From our vantage point on Earth, however, we face a frustrating reality. The object sits in solar conjunction, meaning it appears too close to the Sun in our sky for direct observation. We cannot watch it during these critical hours. The Sun's overwhelming brightness drowns out any attempt to photograph or track the object in real time. This means we must rely on something else, something more subtle and potentially more revealing. Indirect evidence that will only become apparent in the hours and days that follow. What kind of indirect evidence are we talking about? Astronomers will be looking for tiny shifts in trajectory that cannot be explained by gravity alone, excess thermal emissions that suggest active energy release, unexpected outgassing patterns that don't match natural cometary behaviour, or even the release of secondary objects into independent orbits. These would be the signatures of something engineered, something controlled, something intentional. If 3I-ATLAS is more than just a wandering iceberg from interstellar space, if it contains technology, or serves a purpose, then perihelion would be the logical moment to act. This is when velocity peaks, when the gravitational assist from our Sun reaches maximum efficiency, when any applied thrust would yield the greatest possible change in trajectory for the smallest expenditure of energy. Engineers call this the Oberth effect, and if someone built this object, they would know exactly how to exploit it. The tension between what we see in headlines and what scientists actually know has never been greater. Media outlets have been running speculation for weeks, some suggesting this could be humanity's first encounter with alien technology. Avi Loeb, the Harvard astronomer who famously argued that Oumuamua might be artificial, has weighed in with provocative statements about unusual chemical signatures. Public warnings have circulated online, some claiming institutional cover-ups, or suggesting that governments know more than they're sharing. Meanwhile, professional astronomers urge caution, reminding us that extraordinary claims require extraordinary evidence, and that we've been fooled by natural phenomena before. The space between these two positions, between wild speculation and careful skepticism, is where the truth will eventually reveal itself. Consider what we already knew before tonight. Oumuamua, the first confirmed interstellar object discovered in 2017, sparked years of debate about its unusual acceleration and elongated shape. Borisov, the second interstellar visitor found in 2019, behaved like a perfectly normal comet, relieving some of the tension but also disappointing those hoping for something stranger. Now we have 3I-ATLAS, and from the beginning it has presented puzzles that don't quite fit the pattern. Its orbit is nearly aligned with the ecliptic plane, the flat disk where planets orbit our Sun, which is statistically unexpected for a random visitor from the galaxy. Its composition shows anomalies that some researchers find difficult to explain through natural processes alone. Its timing, arriving during an era when humanity finally has the technology to detect and study such objects in detail, feels almost intentional, though that may simply be the cognitive bias of a species desperate for cosmic companionship. Over the next 72 to 240 hours, data will begin flowing in from observatories around the world and from spacecraft positioned throughout the solar system. Astrometric measurements will refine the object's position to millimetre-per-second precision, revealing whether its path deviates from purely gravitational predictions. Spectroscopic observations will analyse the light reflected or emitted by the object, searching for chemical signatures that betray artificial processes. Infrared telescopes will hunt for excess heat that might indicate active systems or propulsion. Radio telescopes will listen for any electromagnetic signals, however faint, that might suggest intentional transmission. Each piece of data will either tighten the case for a natural explanation or crack open the possibility that we are witnessing something unprecedented. The clock is counting down, though by the time you hear these words, perihelion may have already passed. We stand at the threshold of discovery, caught between the comfortable assumption that the universe is empty of other minds and the terrifying, exhilarating possibility that we are being observed, studied, or at least noticed by an intelligence that travelled between the stars. What happens next depends on what the data reveals, but also on how we interpret it, who controls the narrative, and whether humanity is ready to confront the implications of contact, however indirect or ancient it might be. Part 2, First-Order Observations and the Acid Test Metrics. The acid test for 3I-ATLAS comes down to numbers, specifically the numbers that describe how it moves through space. Astronomers will be examining something called delta V, which represents the change in velocity that cannot be explained by gravitational forces alone. Every object in the solar system follows a predictable path determined by the gravity of the Sun and planets, and we can calculate that path with extraordinary precision. If 3I-ATLAS deviates from those predictions by even millimetres per second, sustained over days or weeks, we have a problem that demands explanation. Natural comets do show small non-gravitational accelerations caused by outgassing, when sunlight heats their icy surfaces and releases jets of vapour that act like tiny rocket engines. The question is whether any deviation we observe matches that natural pattern, or suggests something else entirely. An Oberth-style burn would produce a very specific signature in the orbital data. The Oberth effect exploits the fact that kinetic energy increases with the square of velocity, meaning that a small thrust applied when you're moving fastest produces a disproportionately large change in total energy. Perihelion is when 3I-ATLAS moves at maximum speed relative to the Sun, making it the optimal moment for any intentional manoeuvre. If the object fired an engine or released stored energy during these hours, we would expect to see the trajectory begin to deviate in the days that follow, with the deviation growing larger as more data points accumulate. The size of the effect matters enormously. A delta V of 1 millimetre per second would be barely detectable, and could easily be confused with natural outgassing, while a delta V of 1 centimetre per second or more would demand serious attention and multiple independent confirmations before anyone would dare to suggest artificial origins. Measuring such tiny deviations requires extraordinary precision in astrometry, the science of determining the positions and velocities of celestial objects. Ground-based telescopes can achieve positional accuracy of around 0.1 arc-seconds under ideal conditions, which at the distance of 3I-ATLAS translates to uncertainties of hundreds of kilometres. That sounds imprecise, but when you track an object over multiple nights and use statistical methods to fit the observations to a predicted orbit, the accumulated data can reveal velocity changes at the millimetre per second level. The cadence of observations matters. More frequent measurements allow faster detection of anomalies, but also increase the chance of systematic errors creeping into the analysis. The observation windows matter too, because 3I-ATLAS must emerge from behind the Sun before we can resume tracking, and any delay in acquiring fresh data extends the period of uncertainty. Several instruments and tracking networks will be watching for these deviations. The Minor Planet Center coordinates astrometric observations from telescopes worldwide, collecting position measurements and computing updated orbital solutions as new data arrives. Individual observatories contribute their own measurements, which are then cross-checked against predictions to identify outliers or trends. Spacecraft missions operating in the inner solar system might be able to contribute observations from different vantage points, providing parallax measurements that improve position accuracy. Some missions carry instruments sensitive to thermal emissions or capable of imaging faint objects against the background stars. The key is redundancy. If multiple independent observers detect the same anomaly using different instruments and methods, the confidence in the detection rises dramatically. Astronomers will be creating what are called residual plots, graphical representations of the difference between observed positions and predicted positions based on a purely gravitational model. In a perfect world where our model captures every force acting on the object, the residuals would scatter randomly around zero, reflecting only measurement noise. If instead the residuals show a systematic trend, growing steadily in a particular direction over time, that indicates a real physical effect not accounted for in the model. Imagine a graph where each dot represents one night's observation, with the vertical axis showing how far the object's actual position differs from the prediction. If those dots start marching steadily upward or downward, curving away from the zero line in a consistent pattern, you have evidence of an anomaly. The challenge is distinguishing that signal from false alarms caused by modelling errors, unaccounted solar radiation pressure, or subtle errors in the reference star catalogue used to measure positions. False positives represent a constant danger in this kind of analysis. Natural outgassing from a comet can produce accelerations that mimic artificial propulsion, especially if the outgassing is asymmetric or occurs in short bursts. Solar radiation pressure, the gentle push exerted by sunlight on any object with a large surface area relative to its mass, can also produce small accelerations that must be carefully modelled and subtracted. Errors in our assumptions about the object's mass, shape, or reflectivity can propagate through the calculations and create spurious anomalies. What distinguishes a genuine engineered signature from these natural effects? The answer lies in the details. The direction of the acceleration relative to the Sun and the object's motion, the timing of any observed changes, the presence or absence of associated phenomena like dust plumes or thermal emissions, and the consistency of the effect across multiple independent observations. Consider the possibility of observing a plume that doesn't behave like a cometary tail. Normal comet tails are broad and diffuse, pushed away from the Sun by solar radiation and the solar wind, often splitting into separate dust and ion components with different geometries. An engineered plume from a thruster might be narrow and collimated, pointing in a direction that has nothing to do with the Sun, lasting for a short duration, and then shutting off cleanly. If thermal imaging reveals a hot spot that persists longer than ice sublimation physics would predict, or appears in a location inconsistent with passive solar heating, that would be cause for intense scrutiny. The infrared signature of an engine, even a small one, differs from the thermal glow of sunlit ice in ways that spectroscopy can potentially distinguish. The timeline for gathering this evidence stretches across multiple phases. The first data arrives within hours of perihelion, once the object emerges from solar conjunction far enough to be observable again. These initial measurements will be crude, limited by the object's position and brightness, but they will provide the first post-perihelion orbital solution. Daily astrometric updates will refine that solution over the following week, gradually reducing the uncertainty and revealing whether any anomaly exists. Spacecraft observations, if any are scheduled, will arrive on their own timelines, determined by mission operations and data downlink schedules. Some critical measurements might not be available for days or even weeks, during which time speculation will run rampant and competing interpretations will proliferate in scientific circles and public media alike. What would trigger an alert level among astronomers? That depends on the magnitude and clarity of the anomaly. A small deviation that barely exceeds the noise floor might generate private discussions and trigger additional observations, but no public statements until more data confirms or refutes the signal. A large, unmistakable deviation, accompanied by unusual spectroscopic or thermal signatures, would likely prompt rapid coordination through established networks, possibly leading to target of opportunity observations by major facilities and informal communication within the astronomical community before any formal announcement. The boundary between justified caution and excessive secrecy will be tested in real time, with careers and reputations at stake, depending on who claims what and when. Part 3. What we already have in hand, catalogue and imagery. Before we can assess what might happen at perihelion, we need to understand what we already know about 3I-ATLAS from the months of observations leading up to this moment. The object carries the official designation C/2025-1 in the system maintained by the Minor Planet Center, the international clearinghouse for observations of comets, asteroids, and other small bodies in the solar system. That designation tells us it was discovered in the first half of July 2025, making it a relatively recent addition to the catalogue. The astrometric arc, the span of time over which the object has been observed and tracked, now extends across several months, providing a solid baseline for computing its orbit and constraining the uncertainties. Those uncertainties still exist, of course, particularly for an object on such an extreme hyperbolic trajectory, but they have narrowed considerably as more data accumulated. The orbital parameters tell a striking story. The eccentricity measures approximately 6.14, confirming that this is no captured solar system object, but rather a true interstellar interloper. Objects bound to the Sun have eccentricities between 0 and 1, with 0 being a perfect circle and 1 being a parabola that just barely remains bound. Anything above 1 escapes entirely, and 6.14 represents a dramatically hyperbolic trajectory with enormous excess velocity. That excess velocity, the speed at which the object is moving relative to the local standard of rest in the galaxy, comes in around 60 kilometers per second. To put that in perspective, Earth orbits the Sun at 30 kilometers per second, and escaping the solar system from Earth's orbit requires an additional 12 kilometers per second or so. This object arrived with enough speed to blow through our solar system like a bullet through fog, slowing only slightly as it swung around the Sun, and then accelerating back toward interstellar space. The inclination of the orbit measures approximately 175 degrees, meaning it's moving retrograde, in the opposite direction from the planet's motion around the Sun. That alone isn't particularly unusual for interstellar objects, since they arrive from random directions in the galaxy with no preference for our orbital plane. What is unusual, and what has raised eyebrows among researchers, is that the orbital plane aligns closely with the ecliptic, the flat disk defined by Earth's orbit and roughly shared by the other planets. The inclination is only about 5 degrees off from perfect alignment, which is statistically surprising for a random visitor. Most interstellar objects should arrive from arbitrary directions, with inclinations distributed uniformly across all possible angles. Finding one that happens to lie almost exactly in our planetary plane suggests either remarkable coincidence or some kind of selection effect we don't yet understand. Or, as some have speculated, it suggests the object's trajectory was designed to facilitate observation of or interaction with the planets. The imagery we have from pre-perihelion observations comes primarily from Hubble Space Telescope observations, led by astronomer David Jewett and his collaborators. Hubble's sharp vision and sensitivity allowed measurements of the object's nuclear size, though with considerable uncertainty due to the difficulty of separating the solid nucleus from the surrounding dust coma. The observations suggest a nucleus radius somewhere between 0.16 kilometers and 2.8 kilometers, an enormous range that reflects the ambiguity in the data. Other estimates based on different assumptions about albedo, the reflectivity of the surface, have pushed that upper limit even higher. The dust coma brightness indicates moderate activity levels before perihelion, consistent with ice sublimation, but not dramatically higher than other comets at similar distances from the Sun. Nothing in the basic photometry screams artificial, at least not on the surface. One measurement, however, has generated significant discussion in recent weeks. Polarization studies, which examine how light scatters off dust particles in the coma, revealed what researchers described as extreme negative polarization at certain phase angles. polarization measurements are sensitive to the size, shape, and composition of dust grains, and different materials produce distinctive polarization signatures. Most solar system comets show a characteristic polarization curve that reflects the properties of silicate and carbon-rich dust, typical of primitive icy bodies. 3I-ATLAS shows a polarization curve that deviates from that standard pattern, particularly in the negative polarization branch that appears at small phase angles. The authors of a recent paper on the Arciv preprint server noted this anomaly but stopped short of claiming it as definitive evidence of anything unusual, instead suggesting it might reflect unusual dust properties or a composition not commonly seen in solar system comets. Some imagery circulating in online communities claims to show unusual features or structures in enhanced versions of telescope images. These community-circulated enhancements often involve aggressive processing of raw data, boosting contrast and sharpening details in ways that can sometimes reveal genuine features, but also risk creating artifacts or exaggerating noise into apparent structure. Without access to the original unprocessed data and a clear understanding of the processing pipeline, it's impossible to assess whether these enhanced images show anything real. Professional astronomers have been more circumspect, releasing images with careful calibration and error analysis, but those images tend to be more conservative and less visually dramatic than what circulates on social media. The size uncertainty presents a practical challenge for interpreting any anomalies. If the nucleus is small, closer to the lower bound of 0.16 kilometers, then the mass is relatively low, and even modest outgassing or thermal effects could produce detectable accelerations. If the nucleus is large, closer to 2.8 kilometers or beyond, then the mass is much higher, and any non-gravitational acceleration would require correspondingly greater forces to produce. This ambiguity feeds into the error envelope around the predicted orbit. We know the trajectory fairly well, but the exact magnitude of any solar radiation pressure effect or outgassing acceleration depends on parameters we haven't fully constrained. That leaves a certain amount of wiggle room for small deviations to be explained away as natural effects, but it also means that a sufficiently large deviation would stand out unambiguously. The orbital prediction prior to perihelion included uncertainty bands that reflect both measurement errors and modelling uncertainties. Those bands have narrowed over time as more observations accumulated, but they haven't vanished entirely. The tightest constraints come from the most recent measurements before solar conjunction made observations impossible. Now, emerging from behind the Sun, 3I-ATLAS will be reacquired by telescopes and its position measured again. The question is whether that new position falls within the predicted uncertainty band or lies outside it, indicating something unexpected happened during the unobserved hours of perihelion passage. All of this context matters because interpreting any potential anomaly requires understanding what was normal and expected versus what would be genuinely surprising. If the data shows a tiny deviation consistent with the known uncertainties, astronomers will shrug and update their models. If the data shows a large systematic deviation inconsistent with any plausible natural explanation, then we're in uncharted territory, and the acid test has revealed something genuinely extraordinary. Part 4. Spacecraft, Windows and Tactical Follow-ups. Beyond ground-based telescopes, several spacecraft missions operating throughout the solar system may have opportunities to observe 3I-ATLAS in the days and weeks following perihelion. These spacecraft were not designed or positioned with this object in mind, but their trajectories happened to place them in locations where they could potentially acquire valuable data if mission controllers choose to divert attention and resources toward this unexpected target. Each mission faces constraints: power budgets, data storage limits, communication schedules, competing priorities, and operational risks associated with retargeting instruments toward an unplanned object. Whether any of these missions will actually observe 3I-ATLAS depends on decisions being made right now by mission operations teams balancing scientific opportunity against programmatic risk. The European Space Agency's JWST mission, Jupiter Icy Moons Explorer, is currently en route to the Jupiter system via a complex trajectory involving multiple gravity assists from inner solar system planets. JWST's observation window for 3I-ATLAS could open in the days following perihelion, depending on the spacecraft's exact position and orientation. JWST carries a suite of instruments designed for studying icy moons, but capable of turning their attention to other targets. cameras for optical imaging, spectrometers for analysing reflected light, and potentially even radar instruments that could provide unique data on the object's surface properties. The challenge is coordinating such observations with the spacecraft's power and thermal constraints, ensuring that pointing the instruments toward an unexpected target doesn't interfere with critical mission operations or place sensitive hardware at risk. Another significant encounter window opens around November 3rd, 2025, when 3I-ATLAS approaches Venus at a distance of approximately 97 million kilometers. While that distance is far too great for Venus itself to be affected by the object, spacecraft orbiting Venus or monitoring the Venus environment could potentially observe it if their instruments have the necessary sensitivity and field of view. Venus orbiters typically focus on planetary science, studying the atmosphere, surface, and magnetic environment, but their cameras and spectrometers can sometimes be retargeted for brief observations of passing objects. The geometry of this encounter also matters for trajectory analysis. If 3I-ATLAS released secondary objects or experienced a delta V change at perihelion, those effects might become more apparent as the object passes near Venus, and the cumulative deviation from predicted orbit grows larger. Earth's closest approach occurs around December 19th, 2025, at a distance of roughly 1.8 astronomical units, or about 270 million kilometers. This is far from a close encounter in human terms, but it represents the optimal geometry for ground-based observers in the northern and southern hemispheres to acquire high-quality data with professional and amateur telescopes. December observations will benefit from months of accumulated trajectory data, allowing very tight predictions of where the object should be if purely gravitational forces are acting. Any deviation from that prediction will be glaringly obvious by mid-December, assuming the anomaly is large enough to be real. This is also when spectroscopic studies can refine our understanding of the object's composition, searching for chemical signatures that might have been missed or changed during the perihelion passage. The most distant but potentially most revealing encounter window arrives on March 16th, 2026, when 3I-ATLAS passes within approximately 54 million kilometers of Jupiter. NASA's Juno mission, which has been orbiting Jupiter since 2016, could potentially turn its instruments toward the object if the geometry permits and mission controllers deem it worth the effort. Juno's cameras and spectrometers are designed for studying Jupiter's atmosphere and magnetosphere, but they've demonstrated the ability to image other targets, including Jupiter's moons and even distant asteroids. A Juno observation of 3I-ATLAS would provide a dramatically different viewing angle than any Earth-based observation, potentially revealing features or behaviours invisible from our perspective. For each of these mission windows, the type of data that could be collected depends on instrument capabilities and operational constraints. Photometry, the measurement of brightness over time, can reveal rotation rates, activity outbursts, or unexpected dimming events that might indicate fragmentation or debris release. Spectral composition analysis examines the wavelengths of light reflected or emitted by the object, identifying specific molecules or minerals based on their characteristic absorption or emission lines. Trajectory refinement benefits from any additional position measurements, especially from spacecraft located far from Earth, because the parallax provides orthogonal constraints on the orbit. Radio monitoring, if any spacecraft carries suitable receivers, could search for electromagnetic emissions at frequencies that might indicate technological activity, though the chances of detecting anything are vanishingly small unless the object is actively transmitting. The constraints are real and numerous. Communication latency between Earth and distant spacecraft means that any decision to retarget instruments must be made well in advance, often days or weeks before the actual observation window opens. Pointing restrictions exist to protect sensitive instruments from sunlight or to maintain thermal stability. Data downlink schedules are planned months in advance, and inserting unscheduled observations can delay other science, creating friction within the mission team and with the broader scientific community that depends on that mission's data. Mission ops teams must weigh the probability that 3I-ATLAS is genuinely anomalous against the certain cost of diverting resources from planned observations. The timeline for these observations stretches across months, creating a narrative arc that unfolds slowly but inexorably. Perihelion occurs tonight, initiating the cascade of events. Days 1 through 7 after perihelion bring the first post-conjunction observations from ground-based telescopes, establishing whether the object remains on its predicted path or has deviated. Mid-November sees the Venus flyby geometry and potential spacecraft observations, if any have been scheduled. December marks Earth's closest approach and the peak season for amateur and professional follow-up. March 2026 provides the Jupiter window and a final opportunity for spacecraft observations before the object recedes beyond practical observability. Beyond that, months and years of astrometric monitoring will continue, refining the trajectory and searching for long-term deviations that might only become apparent over extended baselines. Risk factors complicate every step of this observational campaign. Ephemeris drift, the gradual accumulation of error in predicted positions, can occur if our models fail to capture all the relevant forces. Space weather events, particularly solar storms that disrupt Earth's ionosphere or interfere with spacecraft operations, can delay or degrade observations. Scheduling conflicts arise when multiple high-priority targets compete for the same telescope time or spacecraft resources. Mission priorities shift in response to unexpected discoveries elsewhere in the solar system, potentially pushing 3I-ATLAS down the queue. Part 5. Immediate Scenarios and the Newsroom Checklist. The next 72 to 240 hours will force us into one of three broad scenarios, each with its own implications and each demanding a different response from the scientific community and the public. Understanding these scenarios ahead of time helps us recognize what we're seeing as the data arrives, and prepares us to respond appropriately rather than reactively. The three scenarios represent different levels of anomaly, from the completely natural to the potentially extraordinary, with ambiguity living in the uncomfortable middle ground where evidence is suggestive but not conclusive. Scenario A is the natural or control case, where 3I-ATLAS behaves exactly as we would expect for an interstellar comet passing through perihelion. This scenario includes fragmentation events, increased outgassing activity as volatile ices sublimate in the intense solar radiation, and small non-gravitational accelerations consistent with cometary jetting. The trajectory deviates slightly from purely gravitational predictions, but the deviation matches models of cometary outgassing both in magnitude and direction. No unusual thermal signatures appear beyond what passive solar heating would produce. No secondary objects are released into independent orbits. Spectroscopic observations reveal a composition that, while perhaps unusual compared to typical solar system comets, can be explained through plausible astrophysical processes in the object's birth environment around another star. In this scenario, 3I-ATLAS joins the small but growing catalogue of interstellar visitors, each one teaching us something about the diversity of planetary systems and the mechanisms that eject debris into the galaxy, but none of them forcing us to confront the possibility of alien technology. Scenario B represents the opposite extreme, a clear, unambiguous engineered signature that cannot be explained through any known natural process. This scenario includes a detectable delta-V anomaly large enough to rule out cometary outgassing, pointing in a direction inconsistent with solar radiation pressure or natural jet activity. It might include a narrow collimated plume, observed during or shortly after perihelion, visible in infrared or optical wavelengths, lasting for a duration suggesting active control rather than passive ice sublimation. Excess thermal emissions might appear in locations or at intensities that cannot be reconciled with solar heating alone. Secondary objects might be released into trajectories that appear targeted towards specific solar system destinations, Venus, Earth, or Jupiter. Spectroscopic analysis might reveal chemical signatures consistent with industrial processes rather than natural astrophysical chemistry, such as highly enriched metallic compounds or molecular species that require energy input to form. In this scenario, the probability that 3I-ATLAS is an artificial object climbs from negligible to substantial, potentially forcing a paradigm shift in how we understand our place in the universe. Scenario C occupies the treacherous middle ground, an ambiguous or borderline result that shows something unexpected but not conclusive. Perhaps the trajectory deviates by an amount that exceeds the expected range of cometary outgassing, but not by enough to completely rule out a rare or extreme natural event. Perhaps thermal emissions show a slight excess that could be explained either by unusual surface properties or by low-level active systems. Perhaps secondary objects are observed, but their trajectories are consistent with normal fragmentation rather than intentional targeting. Perhaps spectroscopic data reveal chemical abundances that are unusual but not impossible through natural processes. In this scenario, astronomers will argue passionately about interpretation, with some favouring exotic natural explanations and others suggesting we cannot rule out artificial origins. Weeks and months will pass as more data accumulates, as alternative models are tested, and as the community tries to reach consensus. This is the scenario that tests institutional integrity, where the pressure to announce something exciting battles against the professional obligation to remain conservative until evidence is overwhelming. If scenario B occurs, if we genuinely detect an engineered signature, the response in the first 24 to 72 hours will be rapid and coordinated, but also chaotic and fraught with uncertainty. Scientists who detect the anomaly will immediately check their data for errors, rerun their analysis with different assumptions, and reach out to colleagues for independent confirmation. If multiple groups detect the same anomaly using different instruments and methods, confidence will grow that the signal is real. At that point, institutional stakeholders must be notified. The International Asteroid Warning Network, NASA's Planetary Defense Coordination Office, ESA's Space Situational Awareness Program, and potentially even SETI organizations or astrobiology centers, depending on the nature of the signature. Who issues the first public alert? That depends on institutional protocols and the personalities involved, but typically the Minor Planet Center or a major observatory might release a circular describing the anomaly without immediately claiming it as evidence of technology. Media attention will explode regardless of how carefully the announcement is worded, forcing scientists into reactive mode as they try to explain complex uncertainties to journalists and the public. If scenario A occurs, if 3I-ATLAS behaves naturally, the narrative shifts toward understanding what we can learn from this particular visitor. Astronomers will declare it an interstellar comet with unusual but explicable properties, and the scientific community will begin preparing papers describing its composition, activity levels, and what those teach us about planetary systems around other stars. Proposals for follow-up missions might arise, suggesting that humanity should develop rapid response spacecraft capable of intercepting future interstellar visitors for close-up study. The public might feel disappointed that we didn't discover alien technology, but the scientific value remains high because every interstellar object provides a window into environments we cannot directly observe. Scenario C, the ambiguous case, presents the hardest communications challenge. How do you convey genuine uncertainty to a public that demands clear answers? How do you maintain transparency without fueling conspiracy theories about cover-ups or institutional bias? The solution requires careful framing, explaining exactly what the data shows, what alternative explanations exist, what additional observations are needed to discriminate between them, and what the timeline looks like for reaching a conclusion. Lower third graphics in video presentations might display labels like preliminary data or multiple interpretations under review to signal that conclusions remain tentative. Scientists must resist pressure to overstate the significance of ambiguous results, while also avoiding excessive conservatism that dismisses potentially important anomalies as noise. A newsroom checklist for covering this story over the coming weeks would include several key elements. First, identify the critical data streams, astrometric residuals from the Minor Planet Center, spectroscopic results from major observatories, spacecraft observation reports if any materialize, and thermal imaging data from infrared telescopes. Second, establish relationships with institutional stakeholders who can provide authoritative information. NASA's Planetary Defense Office, ESA's Space Awareness Coordinators, SETI Institute researchers, and academic groups at institutions with relevant expertise. Third, develop messaging frameworks that balance excitement with caution. Avoid hype that overstates the evidence, but don't dismiss genuinely anomalous results as mundane. Fourth, prepare for the long game, recognizing that definitive conclusions may take months or even years to emerge as accumulated data gradually constrains the possibilities. Consider a specific rapid response scenario. If astrometric data reveals a delta V anomaly exceeding 5 mm per second in a direction inconsistent with cometary outgassing models, and if that anomaly is confirmed by 3 independent observatories within 48 hours of detection, what happens next? SETI might trigger follow-up radio telescope observations, searching for electromagnetic emissions at frequencies that could indicate technological activity. NASA or ESA might convene an emergency panel to assess whether existing spacecraft can be retargeted for closer observations. The International Astronomical Union might issue a special circular alerting the global community to the anomaly and requesting additional observations. Simultaneously, the media storm begins, with journalists demanding interviews, social media amplifying speculation, and public pressure building for official statements. Managing that process requires coordination between scientific institutions, clear communication protocols, and a shared understanding that extraordinary claims will be scrutinized extraordinarily closely before anyone accepts them as fact. Part 6. Chemistry and Weirdness. Composition. Anomalies and what they imply. The chemistry of 3I-ATLAS has been puzzling researchers since the first spectroscopic observations arrived months ago. We are now going to explore what those chemical signatures tell us, what they don't tell us, and why some scientists find them difficult to reconcile with purely natural processes. Chemistry serves as a fingerprint for the environment where an object formed, encoding information about temperature, pressure, radiation levels, and the mix of elements available in that protoplanetary disk billions of years ago. When we analyse light reflected or emitted by 3I-ATLAS, we're essentially reading that fingerprint and trying to match it against what we know about comets born in our own solar system and what we might expect from other stellar environments. The most detailed spectroscopic analysis came from observations using the X-Shooter instrument on the Very Large Telescope in Chile, published in a recent paper in the journal Astronomy and Astrophysics. These observations revealed unusual spectral lines that don't quite match the standard cometry template. Normal comets emit light at specific wavelengths corresponding to common molecules like water vapour, carbon monoxide, carbon dioxide, cyanogen, and various carbon-bearing radicals. 3I-ATLAS shows some of these expected features, confirming that it contains ices and dust like any respectable comet, but it also shows anomalies in the relative abundances of certain species and in the behaviour of those emissions as the object approached perihelion. The extreme negative polarisation measurement mentioned earlier adds another layer of strangeness, because polarisation reflects dust grain properties, and negative polarisation at small phase angles typically requires specific combinations of particle size, shape, and refractive index that don't commonly occur in solar system materials. Polarisation studies work by examining how light waves oscillate as they reflect off particles in the coma. Randomly scattered light becomes partially polarised, with the degree and direction of polarisation depending on the scattering angle and the properties of the scattering medium. For most comets, the polarisation curve follows a predictable pattern: slightly negative polarisation at very small phase angles, crossing through zero, then positive polarisation that increases to a maximum before declining at large phase angles. 3I-ATLAS deviates from this pattern, showing a deeper negative polarisation branch than expected. Some researchers interpret this as evidence for unusual dust composition, perhaps grains with higher metal content or different porosity than typical cometary dust. Others suggest it might indicate an unusual size distribution of particles, with an overabundance of grains in a specific size range that enhances negative polarisation through coherent backscattering effects. Pre-perihelion photometric behaviour provides additional clues about the object's nature. Dust production rates, measured by analysing the brightness and extent of the coma, showed a power law dependence on heliocentric distance that differs slightly from the typical cometary behaviour. Most comets brighten as they approach the Sun according to well-established relationships that reflect how sublimation rates increase with temperature. 3I-ATLAS followed a similar pattern, but with subtle deviations in the power law index that some researchers found intriguing. These deviations might simply reflect unusual ice composition or an unusual distribution of volatiles beneath the surface, where different ices sublimate at different temperatures and distances from the Sun. Alternatively, they might hint at something more exotic, though connecting photometric behaviour to engineered versus natural origins requires enormous leaps of speculation. Several competing interpretations attempt to explain these chemical and physical anomalies within the framework of natural astrophysics. The first interpretation suggests we're seeing a genuinely rare or extreme comet, composition that reflects conditions in its birth environment around another star. Different stars have different metallicities, different ratios of heavy elements to hydrogen, and their protoplanetary disks inherit those compositions. A comet formed in a metal-rich disk might contain higher abundances of refractory materials or unusual mineral phases compared to solar system comets. The negative polarization anomaly might simply reflect that compositional difference, revealing dust grains we've never encountered in our local sample of comets and asteroids. This interpretation requires no exotic physics, only the acknowledgement that the galaxy contains tremendous diversity in planetary system compositions. A second interpretation invokes the thick disk origin hypothesis, suggesting 3I-ATLAS might be a relic from an older generation of stars that formed billions of years ago when the galaxy had different chemical properties. The thick disk of the Milky Way contains older stars with different kinematics and compositions compared to the thin disk where our Sun resides. Objects ejected from thick disk planetary systems might carry chemical signatures reflecting that ancient environment, potentially explaining unusual abundance patterns or dust properties. This interpretation places 3I-ATLAS in a historical context, making it not just an interstellar visitor, but a time capsule from an earlier epoch of galactic evolution. The third and most controversial interpretation suggests the possibility of engineered or manufactured materials producing the observed signatures. This interpretation remains highly speculative and is not supported by peer-reviewed evidence, but it has gained traction in certain circles following public statements by Harvard astronomer Avi Loeb. Loeb has drawn attention to what he describes as unusual nickel emissions in the spectrum, suggesting the possibility of industrial compounds or refined metals rather than natural astrophysical materials. Some media reports have mentioned nickel tetracarbonyl, a volatile organometallic compound used in industrial nickel refining processes on Earth, though no peer-reviewed paper has confirmed the detection of this specific molecule in 3I-ATLAS. The claim remains unverified and should be treated with extreme skepticism until independent groups reproduce the observation and rule out alternative explanations. Laboratory analogues help us understand what different compositions might look like in spectroscopic and polarimetric observations. Terrestrial industrial processes that produce pure metal compounds follow well-characterized chemical pathways that require specific conditions: controlled atmospheres, precise temperatures, catalysts, and energy inputs. Natural astrophysical environments can produce metal-rich materials through processes like condensation in stellar outflows, or high-temperature chemistry in protoplanetary disks, but the resulting materials typically show mixtures of phases and oxidation states rather than the refined single-compound signatures characteristic of industrial processing. If spectroscopic analysis genuinely revealed highly pure metallic emissions without the expected complement of oxidized forms or mixed phases, that would be difficult to explain through natural processes and would legitimately raise questions about artificial origins. The Bayesian framework for evaluating these competing hypotheses requires us to consider both the likelihood of observing particular data given each hypothesis and the prior probability we assign to each hypothesis before seeing the data. If we start with extremely low prior probability for engineered origins, as most scientists do, then even moderately unusual chemical signatures don't substantially shift our posterior probability toward the artificial hypothesis unless those signatures are so extreme and specific that natural explanations become vanishingly unlikely. This is why the burden of proof is so high for extraordinary claims. Our priors matter, and overcoming a very low prior requires overwhelmingly strong evidence, not just suggestive anomalies. The question that keeps circling back is this: if you detect chemistry that deviates significantly from solar abundance patterns and from the range observed in solar system comets, at what point does that deviation become compelling evidence for non-natural origins? The answer depends on how well we understand the diversity of possible natural environments. Our sample size of comets from other stellar systems remains tiny, just 3 confirmed objects, so we have almost no empirical basis for knowing what's normal versus anomalous for interstellar visitors. Until we build that statistical baseline through future detections, every unusual measurement could be either a genuine anomaly pointing towards something extraordinary, or simply a reminder that the universe is more diverse than our limited local sample suggests. The chemistry puzzle connects directly to the propulsion question, because any engineered thrust system would likely leave chemical signatures in its exhaust or waste heat. If 3I-ATLAS is more than a passive rock, if it contains systems capable of altering its trajectory, then those systems must produce observable effects: expelled propellant, thermal emissions, electromagnetic signatures, or structural changes. The chemical weirdness we've observed so far doesn't conclusively point in either direction, but it establishes that this object is unusual enough to warrant careful scrutiny as we search for mechanical or energetic signatures in the post-perihelion data. Part 7. If it's engineered, propulsion architectures at 1.4 AU. Suppose for a moment that 3I-ATLAS is not a passive interstellar iceberg, but rather an object containing systems capable of altering its trajectory in deliberate ways. What kind of propulsion architecture would be feasible at perihelion 1.35 to 1.4 astronomical units from the Sun, and what observational signatures would such a system produce? This question requires us to think through the engineering constraints and possibilities, not because we have any confirmed evidence of artificial propulsion, but because understanding what to look for helps us recognise it if it appears in the data. The challenge is enormous. Any propulsion system must operate in the extreme environment near the Sun, must produce enough thrust to create a detectable trajectory change, and must do so using energy and propellant mass that the object can carry or generate. High specific impulse chemical propulsion represents the simplest and most familiar architecture, analogous to rocket engines used in human spaceflight. A chemical rocket combines fuel and oxidizer, releases energy through combustion, and expels the hot exhaust at high velocity to generate thrust. Specific impulse, measured in seconds, quantifies the efficiency of the engine, with higher values meaning you get more thrust from each kilogram of propellant. Chemical rockets typically achieve specific impulses in the range of 200 to 450 seconds, respectable for manoeuvring spacecraft but requiring substantial propellant mass for large velocity changes. If 3I-ATLAS carried a chemical propulsion system and fired it at perihelion, we would expect to see a narrow directed plume of hot gas expelled in the direction opposite to the desired thrust vector. The exhaust would glow in infrared wavelengths due to its high temperature, potentially producing an observable thermal signature lasting for minutes to hours depending on burn duration. Astrometric measurements would reveal a sudden velocity change in the predicted direction, growing larger over subsequent days as the object moves along its altered trajectory. Pulsed thermal engines represent a more exotic option that exploits solar energy rather than stored chemical energy. A solar thermal rocket uses mirrors or lenses to concentrate sunlight onto a heating chamber, raising the temperature of a working fluid that then expands through a nozzle to generate thrust. At one point, 4 AU, solar intensity is diminished compared to Earth's orbit but still substantial, around 500 watts per square metre. A large enough collector area could gather megawatts of power, heating propellant to temperatures high enough for useful specific impulse. The advantage of solar thermal propulsion is that you don't need to carry fuel, only propellant mass, and you can potentially use any volatile material, even water ice or carbon dioxide sublimating from the object's own surface. The observable signature would include thermal emissions from the collector surface, directional outgassing as propellant expands through the nozzle, and trajectory changes consistent with the thrust vector. The challenge is building a system with sufficient collector area and thermal engineering to handle the concentrated sunlight without melting or degrading. Directed mass ejection through electromagnetic acceleration provides another speculative possibility. A mass driver or railgun uses electromagnetic forces to accelerate projectiles to high velocity, expelling them to generate thrust through conservation of momentum. Unlike chemical or thermal rockets that expel hot gas, a mass driver launches solid or liquid pellets at velocities potentially reaching kilometers per second. The specific impulse can be very high, meaning less propellant mass is required for a given velocity change, but the system requires substantial electrical power to operate. At perihelion, solar panels could potentially generate that power, converting sunlight into electricity that drives the acceleration system. The observable signature would include the expelled mass itself, potentially visible as a stream of small particles trailing behind the object, and electromagnetic emissions associated with the acceleration pulses. Trajectory analysis would reveal velocity changes consistent with the momentum transfer from expelled mass. Beam-driven propulsion represents an even more speculative architecture where external energy beams, possibly lasers or masers, illuminate the object and impart momentum through radiation pressure or ablation. This scenario requires infrastructure elsewhere in the solar system or in nearby interstellar space. a powerful transmitter capable of delivering megawatts or gigawatts of power across astronomical distances and maintaining precise targeting of a fast-moving object. The advantage is that the object itself doesn't need to carry fuel or power systems, only a surface capable of absorbing or reflecting the beam efficiently. The observable signature might include unexpected heating on one side of the object, asymmetric thermal emissions, or small but sustained accelerations in a consistent direction over extended periods. This architecture seems implausible given the enormous distances and energies involved, but we include it for completeness because ruling it out requires understanding what we should or shouldn't observe. For each propulsion concept, we can estimate the required energy budget and compare it to what's physically plausible. Consider a delta V of 1 centimeter per second, applied at perihelion to an object with mass of 10 to the 15 kilograms, roughly consistent with a nucleus radius of 1 kilometer and typical cometary density. The kinetic energy change equals 1/2 times mass times velocity change squared, yielding approximately 10 to the 11th joules. That's a modest energy compared to, say, chemical explosives or nuclear reactions, but it must be delivered in a controlled directional manner. Chemical propellant could provide that energy if the object carried sufficient fuel, perhaps a few percent of its total mass depending on specific impulse. Solar thermal propulsion could deliver it over a longer burn duration using concentrated sunlight. The key question is whether any plausible natural process could mimic those signatures. Outgassing jets can produce accelerations in that range, but typically with different temporal profiles and directional properties than engineered thrust. The waste heat signature matters enormously for detection. Any propulsion system operates with less than perfect efficiency, converting only a fraction of input energy into useful kinetic energy, while the remainder becomes waste heat that must be radiated away. A chemical rocket at typical temperatures radiates predominantly in the mid-infrared, around 3 to 15 microns wavelength. Solar thermal systems have cooler exhaust and hotter collector surfaces, potentially showing distinct thermal signatures in multiple infrared bands. Mass drivers generate waste heat in the acceleration system and potentially in the expelled projectiles if they're heated during launch. Beam-driven systems heat the illuminated surface, creating hotspots that radiate thermally. Each of these heat sources produces characteristic spectral signatures that infrared spectroscopy can potentially distinguish from passive solar heating of an inert surface. Plume geometry provides another diagnostic. Natural cometary jets are typically broad and chaotic, driven by sublimation from multiple active regions on the nucleus, with dust and gas expanding radially away from the surface and then being pushed by solar radiation pressure and the solar wind. An engineered plume from a thruster should be more collimated, expanding in a cone with opening angle determined by nozzle design, potentially showing shock structures or density gradients characteristic of supersonic flow. High-resolution imaging during or shortly after a burn might reveal these geometric differences, allowing us to distinguish between passive outgassing and active propulsion. The directionality matters too. Cometary jets typically point away from the sun because that's where sunlight heats the surface most intensely, while engineered thrust can point in any direction, depending on mission requirements. Potential debris or secondary ejecta complicates the picture. If an object fires a propulsion system, especially one involving mechanical components or high-energy processes, it might shed fragments or expel material not intended as propellant. These debris pieces would follow ballistic trajectories determined by their ejection velocity in the gravitational field, potentially becoming detectable as small objects orbiting independently or trailing behind the primary object. Finding such debris would be strong evidence of mechanical activity, though distinguishing it from natural fragmentation requires careful analysis of the debris trajectories and compositions. The objection that arises immediately is, if this object is engineered, why would it hide its capabilities? Why not transmit signals or perform maneuvers so obvious that we couldn't miss them? Several answers exist, though all are speculative. Perhaps the object is old and damaged, operating with minimal functionality rather than full design capability. Perhaps it's designed for stealth, minimizing detectable signatures to avoid attracting attention from potential threats. Perhaps its mission doesn't require communication with indigenous civilizations, only passive observation or data collection that proceeds regardless of whether we notice. Perhaps the maneuvers are actually obvious by advanced civilization standards, and we simply lack the instrumentation or knowledge to recognize them clearly. Each of these explanations requires accepting premises about alien intentions and capabilities that we have no way to verify, which is why evidence must drive conclusions rather than speculation about motives. Part 8. Mini-probe, seeding hypothesis and trajectory archaeology. Now we enter speculative territory that pushes the boundaries of what's scientifically responsible to discuss, but that nonetheless captures the imagination and deserves careful analysis. Suppose 3I-ATLAS is not merely passing through our solar system, but actively depositing smaller objects, microprobes or sensors, into orbits that target specific destinations: Venus, Earth, Mars, Jupiter. What would such a seeding operation look like? How would we detect it? What would the dispersed objects do once they reach their targets? These questions blend engineering analysis with profound speculation about possible intentions, creating a scenario that science fiction has explored for decades, but that serious science must approach with extraordinary caution. The scenario begins with a deployment event at or near perihelion, when 3I-ATLAS occupies the optimal position for releasing objects that could subsequently reach inner or outer solar system destinations with minimal additional velocity change. The Obert effect works in reverse here too. A small velocity change imparted to a secondary object at perihelion, when relative velocities are highest, translates into a large energy change that opens up a wide range of possible destination orbits. A release velocity of just a few meters per second could send fragments on trajectories that intersect planetary orbits months or years later, depending on the specific direction and timing of release. The challenge from an engineering perspective is achieving precise targeting. Hitting a specific planet at a specific future date requires careful calculation of release parameters and potentially some ability to make mid-course corrections. Working through the orbital mechanics, we can reverse integrate possible trajectories to understand what release conditions would be required for intercepts with Venus, Earth, or Jupiter during the observational windows we've already identified. Venus approach occurs around November 3rd, just 5 days after perihelion, at a distance of 97 million kilometers. For a small object released at perihelion to reach that geometry, it would need to be released with a velocity component that slightly alters its perihelion distance and timing so that it crosses Venus's orbital path at the right moment. The required delta V depends on exactly where Venus is in its orbit at the time, but ballpark estimates suggest a few meters per second to tens of meters per second would suffice. That's within the range that simple mechanical ejection could provide. A spring-loaded release mechanism, a small gas thruster, or even sublimation-driven outgassing if cleverly directed. Jupiter approach on March 16, 2026, lies much farther in the future and requires different orbital dynamics. An object released at perihelion with appropriate velocity could enter an orbit with slightly different semi-major axis and eccentricity, such that it reaches aphelion, its farthest point from the Sun near Jupiter's orbital distance, at roughly the same time Jupiter passes through that region. The delta V required increases with the precision of targeting. Hitting within 1 million kilometers of Jupiter is relatively easy. Hitting within 100,000 kilometers requires more precision and potentially more velocity change. The interesting question is whether released objects would merely pass near Jupiter or actively attempt rendezvous with specific moons like Europa or Ganymede, where subsurface oceans might harbour conditions suitable for life. Achieving close moon encounters requires substantially more delta V and much more sophisticated guidance. The expected observational footprint of such a seeding operation depends critically on the size and number of released objects. If we're talking about dust-sized particles, they would be effectively invisible unless they're extremely numerous or happen to pass very close to Earth or a spacecraft. If we're talking about centimetre to metre scale objects, they might be detectable through reflected sunlight or thermal emissions, but only with dedicated searches using sensitive instruments. If we're talking about larger objects tens of metres across, they would show up in sky surveys as new asteroids or cometary fragments, triggering alerts from automated detection systems. The trailing debris cloud structure would provide clues. A natural fragmentation event typically produces a cloud of particles that slowly spreads out along the parent object's orbit, while a directed release of multiple objects on different trajectories would produce a more complex non-symmetric distribution. Astronomers and amateur observers could search for this debris using several approaches. Enhanced photometry around the Venus proximity window would look for sudden brightness changes, or new point sources appearing near the predicted position of 3I-ATLAS or offset from it by amounts, consistent with release during perihelion. Radar observations from planetary radar systems like the Arecibo dish, if it were operational, or the Goldstone facility, could detect small objects passing within a few million kilometres of Earth by bouncing radio waves off them and analysing the reflected signal. Occultation searches monitor bright background stars for momentary dimming events, caused by foreground objects passing through the line of sight, potentially revealing otherwise invisible debris. Automated sky surveys that imaged large areas of sky repeatedly could spot moving objects that weren't present in earlier images, triggering follow-up observations to determine their orbits. The scale of such an operation remains pure speculation. Are we hypothesizing thousands of microprobes scattered throughout the solar system? A few dozen strategically placed sensors targeting high-priority locations? A single probe released toward Earth with the rest being natural fragmentation debris? Each scenario produces different observational signatures and requires different levels of technological sophistication. Thousands of objects imply an industrial-scale capability, and perhaps a civilization accustomed to sending massive survey missions. A few objects suggest a more targeted, efficient approach, prioritizing specific destinations based on prior knowledge. The number of objects also affects detection probability. More objects mean more chances for one to pass close enough to Earth, or a spacecraft to be noticed, but also more chances for amateur astronomers to spot something unusual. Could existing spacecraft be retargeted to search for unusual small objects near Venus or Jupiter during the relevant windows? In principle, yes, but in practice the challenges are severe. Spacecraft cameras and instruments have limited fields of view and must be pointed precisely at targets to acquire useful data. Searching for unknown objects in the vast volume of space near a planet requires either systematic surveys covering large areas, which are time-consuming and data-intensive, or prior knowledge of where to look, which we don't have unless ground-based observations provide rough positions. The missions currently operating near Venus and Jupiter were designed for planetary science, not for hunting debris, and their operational plans are packed months in advance with observations of the planets and moons they were sent to study. Diverting resources towards speculative debris searches requires convincing mission managers that the probability of finding something interesting justifies the cost in lost planetary science. The speculative motivation question cannot be avoided, even though answering it requires anthropomorphic assumptions about alien psychology and decision-making. Why would an advanced civilization dispatch microprobes from an interstellar object passing through a planetary system? Reconnaissance is the obvious answer, gathering data about planetary environments, atmospheric compositions, surface conditions, and potentially biological signatures if life exists. Seeding in the literal sense might involve depositing self-replicating machines that establish a persistent presence, gathering data over centuries or millennia, and potentially transmitting it back to the civilization of origin using techniques we can't currently imagine. Communication relay nodes could establish a network allowing real-time or near-real-time monitoring of the system, though the time lag for signals to cross interstellar distances makes real-time a misleading term. Each of these motivations assumes that the civilization values knowledge about other planetary systems, an assumption that seems reasonable given that we value such knowledge ourselves, but remains fundamentally unverifiable. The most unsettling possibility is that we're interpreting the entire scenario incorrectly, projecting human exploration motives onto phenomena that operate according to completely different logic. Perhaps the object isn't exploring at all, but rather serving some industrial or logistical function we can't recognize, collecting specific materials from the solar environment, disposing of waste products from some interstellar operation, or testing technologies in the harsh environment near a star. Perhaps the releases aren't probes, but rather artifacts of natural processes we haven't yet characterized. Unusual outgassing patterns or electrical phenomena that produce signatures superficially similar to engineered deployment. Distinguishing between these possibilities requires not just detecting anomalies, but understanding them mechanistically, demonstrating that natural explanations fail comprehensively before accepting extraordinary interpretations. Part 9. Community and Institutional Dynamics, Credibility, Data Policy and Conspiracies. The social dimension of this story matters as much as the technical details, because how humanity responds to ambiguous evidence depends critically on institutions, individuals, and the complex web of incentives that shape scientific communication and public understanding. The possibility that 3I-ATLAS might be something other than a natural comet triggers dynamics that go far beyond normal astronomical research, activating deep-seated hopes and fears about contact with alien intelligence, testing the robustness of scientific institutions designed for incremental discovery rather than paradigm-shattering revelations, and exposing the fault lines between expert consensus and public speculation. Understanding these dynamics helps us anticipate what might happen in the coming days and weeks, regardless of what the data ultimately shows. Public fascination with alien technology claims has intensified over the past decade, driven by the Oumuamua controversy, renewed interest in unidentified aerial phenomena following government declassifications, and the growing catalogue of exoplanets demonstrating that planets around other stars are common rather than rare. Skepticism culture has evolved in parallel, with many people reflexively dismissing extraordinary claims as either misidentified natural phenomena or deliberate hoaxes, while others embrace those claims enthusiastically, interpreting any ambiguity as confirmation of their priors. The Oumuamua debate set the template. Harvard astronomer Avi Loeb argued publicly that the object's unusual acceleration might indicate artificial origins, perhaps a light sail or other technology, while most astronomers countered that natural outgassing provided a simpler explanation requiring no exotic physics. The debate played out in scientific journals, popular media, and social media platforms, with passionate advocates on both sides and a large middle ground of researchers who found the controversy more distracting than illuminating. The stakeholder network for tracking and responding to anomalies like 3I-ATLAS spans multiple organisations and communities, each with its own priorities and constraints. Professional astronomers at research institutions and observatories conduct the observations and analysis that provide the raw data, motivated by scientific curiosity, career advancement through publications, and the intellectual challenge of understanding unusual phenomena. The Minor Planet Center coordinates astrometric campaigns, collecting position measurements from observatories worldwide and computing updated orbital solutions that track how objects move through the solar system. The International Asteroid Warning Network, established to coordinate responses to potentially hazardous asteroids, provides a framework for rapid communication and data sharing when unusual objects are detected, though its mandate focuses on impact risk rather than technological signatures. NASA's Planetary Defense Coordination Office and ESA's Space Situational Awareness Program monitor near-Earth objects and coordinate international responses, bringing governmental resources and institutional legitimacy to the effort. SETI organisations and astrobiology centres occupy a unique position in this network, focused specifically on searching for evidence of extraterrestrial intelligence or life. These institutions have developed protocols and technical capabilities for detecting potential technosignatures, from radio transmissions to optical laser pulses, and they maintain relationships with observatories that can be activated when interesting targets emerge. The challenge they face is balancing the genuine scientific search for intelligence against the risk of being associated with fringe speculation or pseudoscience, a reputational threat that makes many SETI researchers extremely conservative about what claims they're willing to make publicly. Media influencers and private space enthusiast voices add another layer to the network, amplifying certain interpretations and framing, narratives that may or may not align with scientific consensus. Avi Loeb, for example, has built a substantial public platform partly through his willingness to discuss exotic possibilities that most astronomers avoid, attracting both admirers who appreciate his intellectual courage and critics who accuse him of seeking attention through sensationalism. Formal tracking and reporting practices follow established protocols that balance the need for rapid communication with the requirement for data quality and verification. When an observer detects an unusual object or notices anomalous behaviour in a known object, they typically report it to the Minor Planet Center, using standardized formats that include position measurements, timestamps, observer details, and preliminary orbital calculations. The Minor Planet Center staff review these reports, check them for errors or inconsistencies, and if satisfied, incorporate them into the official database and potentially issue a Minor Planet electronic circular announcing the discovery or unusual activity. Emerging anomalies that might indicate something beyond normal, cometary or asteroid behaviour, trigger informal communications among researchers, often through email lists or collaboration platforms where experts share preliminary findings and coordinate follow-up observations. Official announcements wait until multiple independent confirmations establish that the anomaly is real rather than an artifact of measurement error or data processing mistakes. Some claims circulating in online communities about 3I-ATLAS have not been verified through these formal channels. Reports of unusual coloration, descriptions of the object as Manhattan-sized, and claims that it appears on special watch lists maintained by AN or other organisations lack direct institutional documentation that would confirm them. This doesn't necessarily mean the claims are false, but it does mean they should be treated with caution until corroborating evidence emerges. The problem is that once unverified claims circulate widely, especially through social media platforms where attention and engagement drive visibility, they can shape public perception and create pressure on institutions to respond even when the underlying information is questionable. Scientists then face a difficult choice: ignore the claims and risk being accused of cover-up, or address them directly and potentially give them more attention and legitimacy than they deserve. The tension between transparency and caution runs through every aspect of how institutions manage potentially extraordinary discoveries. Transparency demands sharing data and findings openly, allowing independent verification and building public trust through honesty about what is known and unknown. Caution demands withholding announcements until evidence reaches a high threshold of confidence, avoiding false alarms that damage credibility and create confusion. When data shows something odd, something that doesn't fit standard models but isn't yet conclusive, institutions face real dilemmas about what to say and when. Delaying announcements to allow time for verification can fuel speculation about cover-ups or conspiracies, especially if rumours leak through informal channels before official statements emerge. Rushing to announce preliminary findings risks amplifying noise into signal, turning measurement artifacts or rare natural phenomena into major controversies that consume time and resources to resolve. Historical examples illustrate both the dangers and the potential of these dynamics. The fast radio burst phenomenon initially generated speculation about alien signals because the bursts appeared to show temporal patterns that some interpreted as artificial, but further observations revealed that most or all of them arise from natural astrophysical sources like magnetars. The supposed detection of phosphine in Venus's atmosphere triggered intense excitement about possible biological activity, but subsequent reanalysis cast doubt on whether the detection was real or resulted from data processing choices and instrumental artifacts. The SETI false alarm from BLC-1, a candidate radio signal detected by the Breakthrough Listen project, generated brief intense interest before being traced to human-generated interference rather than extraterrestrial transmission. Each case demonstrates how initial excitement must give way to careful verification before conclusions solidify. The motives driving different actors in this system vary considerably. For individual researchers, being first to detect or correctly interpret something extraordinary brings enormous professional rewards: publications in prestigious journals, invitations to conferences and media appearances, enhanced reputation among peers, and potentially long-term career advantages. The flip side is the reputational damage from making claims that don't hold up under scrutiny. Being remembered as the person who cried alien when the truth was far more mundane. For institutions, the incentives favour caution, because credibility accumulated over decades can be destroyed by a single high-profile mistake. The media faces different incentives entirely, rewarded for attention and engagement rather than accuracy, which can create pressure to hype ambiguous results or frame stories in ways that maximise emotional impact rather than careful understanding. Speculative scenarios about internal conflicts or competing agendas add another dimension of uncertainty. What if one group of observers detects an anomaly, but decides to keep it quiet until spacecraft data arrives that could provide definitive confirmation or refutation? What if commercial space interests with investments in interstellar mission concepts push for early public hype to generate interest and funding, even when the evidence remains ambiguous? What if government agencies with classified observational capabilities know more than they're sharing but remain silent due to national security considerations, or simply because confirming extraordinary claims outside the usual scientific channels would be too disruptive? These scenarios are largely speculative, unsupported by concrete evidence, but they illustrate the complex landscape of power, information flow, and institutional dynamics that shapes how discoveries become public knowledge. The visual and documentary evidence that accompanies any developing story matters for shaping public understanding. Archival footage of past scientific controversies, from cold fusion announcements to claims of fossilized bacteria in Martian meteorites, reminds us that the boundary between revolutionary discovery and embarrassing error is sometimes visible only in retrospect. Media headlines oscillate between uncritical enthusiasm and dismissive skepticism, rarely capturing the nuanced middle ground where most genuine scientific progress occurs. Screenshots of institutional web pages and official reports provide verifiable touchstones, allowing interested observers to check claims against primary sources rather than relying on second-hand interpretations. Interviews with astronomers expressing caution versus curiosity reveal the diversity of opinion within the scientific community, challenging the notion that scientists speak with a single voice or reach consensus easily on controversial topics. The drama surrounding how data is collected, interpreted, and communicated matters even if 3I-ATLAS turns out to be entirely natural, because the process itself reveals how prepared or unprepared humanity is for genuinely anomalous discoveries. The protocols we develop, the communication channels we establish, the levels of transparency and verification we demand, all of these will shape our response when someday, perhaps not today but eventually, we encounter something that genuinely cannot be explained through natural processes alone. Building that infrastructure requires practice, learning from near misses and false alarms, refining our ability to separate signal from noise, and to communicate uncertainty without either paralysis or premature certainty. Part 10. The hardest question: intention and interpretation. Suppose you wake up tomorrow and learn that astrometric data confirms a small but statistically significant anomaly in the trajectory of 3I-ATLAS, something that cannot be explained through natural outgassing or modelling errors, something that genuinely suggests active control. What then? How do you infer intention from observation? How do you leap from detecting an anomaly to understanding why it exists, what purpose it serves, what intelligence, if any, lies behind it? These questions probe the deepest epistemological challenges in the search for extraterrestrial intelligence, forcing us to confront how much we can actually deduce about minds utterly different from our own based on fragmentary physical evidence. The answers matter because they shape how humanity would respond, what risks we might face, and what opportunities might exist if contact, however indirect, has truly occurred. A ladder of inference connects raw observation to interpreted meaning, with each step requiring assumptions and judgments that become increasingly speculative as you climb higher. The first rung is the anomaly itself, a measured deviation from predicted trajectory, an excess thermal emission, a chemical signature inconsistent with known natural processes. This rung demands careful statistics and error analysis, but remains largely objective, answerable through standard scientific methods. The second rung is magnitude and directionality. How large is the anomaly? In what direction does it point? When exactly did it occur? These properties provide clues about mechanisms, constraining the range of possible explanations, both natural and artificial. The third rung is possible motive. If the anomaly reflects intentional action, what goal might it serve? This is where speculation truly begins, because inferring purpose requires modelling the decision-making of an intelligence whose evolutionary history, technological capabilities, and value systems remain completely unknown. Plausible motives span a wide range of possibilities, each leading to different predictions about what we should observe. An observer probe would prioritise gathering data about the solar system, its planets, and potentially its inhabitants, using sensors to record electromagnetic emissions, atmospheric compositions, surface features, and any signs of technology or biology. Such a probe might remain passive, avoiding actions that would reveal its presence, or it might actively transmit data back to its origin civilization using laser pulses or radio signals. A remote sensor network might involve multiple distributed objects positioned to provide comprehensive coverage of the solar system, triangulating on interesting phenomena or monitoring long-term changes over years or decades. Reconnaissance suggests a more active mission with specific intelligence-gathering objectives, perhaps assessing habitability of planets, cataloguing resources, or even evaluating technological capabilities of any civilizations present. Seeding or breadcrumb scenarios imply a longer-term strategy, where the visiting object deposits monitors or artifacts that remain in the solar system after the primary object departs, establishing a persistent presence that continues functioning long after the initial encounter. These monitors might activate under specific conditions, for example when they detect electromagnetic emissions characteristic of technological civilization, or they might operate continuously gathering data and storing it for eventual retrieval or transmission. The advantage of seeding is redundancy and coverage. Multiple monitors in different locations provide backup and complementary perspectives, ensuring that even if some fail or are destroyed, others continue the mission. Testbed or experiment scenarios suggest the object is actively manipulating conditions or observing responses to stimuli, treating the solar system as a laboratory for studying planetary system dynamics, astrobiological processes, or perhaps sociological responses to contact stimuli. Communication relay or signal repeater functions would allow the object to serve as infrastructure for interstellar communications, either relaying messages between distant civilization or providing a navigation beacon that helps other objects find their way through interstellar space. This interpretation assumes the existence of broader networks or traffic patterns that we haven't detected, an infrastructure of interstellar civilization that operates on scales and timescales beyond our current observational reach. The relay function might activate only when specific signals are received, remaining dormant otherwise to conserve energy and avoid detection. Completely passive relics represent the null hypothesis for technological artifacts, objects built long ago that no longer function as originally intended, but continue moving through space on ballistic trajectories determined by their last active maneuver. A passive relic might contain information or structure that reveals its artificial origins but lack any active systems capable of observation, communication, or maneuver. Detecting such a relic would still be scientifically revolutionary, proving that technological civilizations exist or existed elsewhere in the galaxy, but would not pose any immediate risks or opportunities for interaction since the relic cannot respond to our presence. Adaptive or responsive probes represent the most sophisticated and potentially concerning scenario. Objects equipped with artificial intelligence or autonomous decision-making systems that can observe their environment, recognize patterns or targets of interest, and modify their behavior accordingly. An adaptive probe might detect Earth's electromagnetic emissions, recognize them as technosignatures indicating technological civilization, and alter its trajectory or actions to optimize observation of humanity. Such a probe might release secondary objects targeted specifically at Earth after recognizing it as particularly interesting, or it might transmit signals alerting its origin civilization to the presence of another intelligence. Part 11. LIGO Observation. 4. New Black Hole. Merger results and observation readiness. While 3I-ATLAS dominates headlines and occupies telescope time around the world, other extraordinary discoveries continue reshaping our understanding of the universe at scales both larger and stranger than interstellar visitors. The fourth observing run of LIGO, the Laser Interferometer Gravitational Wave Observatory, along with its international partners Virgo and Cagra, has been detecting mergers of black holes and neutron stars throughout 2025, adding to the catalogue of gravitational wave events that now numbers in the hundreds. These detections might seem unrelated to the question of whether 3I-ATLAS is natural or engineered, but the connection runs deeper than it first appears, revealing how humanity has developed rapid response networks capable of coordinating observations across multiple instruments and institutions within minutes of an unexpected event. The most recent black hole merger announcements from the 04 run showcase the maturity of gravitational wave astronomy as a field. When LIGO's detectors register the characteristic chirp signal of two black holes spiraling together and merging, automated systems immediately analyze the data to determine the sky location of the event, compute the uncertainty region, and distribute alerts to astronomical observatories around the world. Telescopes across multiple wavelengths from gamma ray to radio receive these alerts and can slew to point at the sky region within seconds or minutes, searching for electromagnetic counterparts that might accompany the gravitational wave signal. For black hole mergers, electromagnetic counterparts are rare because black holes typically don't have much surrounding material to emit light, but for neutron star mergers, the ejected material produces spectacular optical, infrared, and gamma ray signals that provide complementary information about the physics of the merger. The rapid alert infrastructure that makes this multi-messenger astronomy possible has been refined over multiple observing runs, learning from failures and successes to optimize the process. When a gravitational wave candidate is detected, the LIGO-Virgo-CAGRA collaboration issues automated alerts through established channels that observatories have subscribed to, typically within minutes of the detection. These alerts include preliminary sky localization, estimates of the source properties like masses and distance, and assessments of the probability that the signal is astrophysical rather than instrumental noise or glitches. Observatories receiving the alerts use their own decision algorithms to determine whether to interrupt ongoing observations and retarget toward the gravitational wave source, balancing the scientific value of catching a rare electromagnetic counterpart against the cost of abandoning planned observations. The organizational structure supporting this rapid response involves agreements between institutions, allocation of dedicated observing time for transient follow-up, development of software tools for automated decision-making, and crucially, trust built through years of collaboration. Astronomers know that false positives occur, that not every gravitational wave alert will produce visible electromagnetic signals, but they've developed protocols for managing those uncertainties and sharing risk across the community. The result is a global network capable of responding to unexpected events, with a coordination and speed that would have been impossible just a decade ago. This infrastructure provides a template for what we might need if 3I-ATLAS or any future object shows genuinely anomalous behavior requiring rapid follow-up. Imagine an equivalent alert channel for interstellar object anomalies. When astrometric measurements reveal a trajectory deviation exceeding some threshold, automated systems could distribute alerts to SETI radio telescopes, infrared observatories, spacecraft missions with flexible scheduling, and ground-based imagers capable of acquiring high-resolution follow-up data. Observatories would receive not just the alert, but also predictions of where to point and what wavelengths to prioritize based on the specific nature of the anomaly. Within hours rather than days or weeks, multiple independent observations could confirm or refute the anomaly and begin characterizing its properties. The challenge is that building such infrastructure requires investment and coordination across organizations that don't currently have strong reasons to collaborate on interstellar object observations. LIGO and its partners developed their rapid response network because gravitational wave detections are rare and valuable, and because electromagnetic follow-up provides scientific information that gravitational waves alone cannot deliver. For interstellar objects, most will be natural and uninteresting from a techno-signature perspective, making it harder to justify dedicating resources to automated follow-up systems. The argument for building that infrastructure rests on the asymmetric payoff. If even one object in 100 or 1,000 turns out to be genuinely artificial, detecting it and characterizing it before it leaves the solar system could be the most important scientific discovery in human history. The specific O4 results that have been announced recently include mergers spanning a range of black hole masses, from stellar mass binaries formed from massive stars to intermediate mass black holes that might form through different channels. Each detection refines our understanding of the population of black holes in the universe, their formation mechanisms, and the astrophysical environments that bring them together to merge. Some events show hints of spin alignment or misalignment that provide clues about how the binary systems formed, whether through evolution of isolated binaries or through dynamical capture in dense stellar environments. The accumulated catalogue now allows statistical analyses that were impossible with just a handful of events, revealing patterns and trends that test theoretical predictions. One particular case in O4 demonstrated the power of rapid multi-wavelength follow-up, when a neutron-star merger candidate triggered alerts to telescopes around the world. Multiple observatories detected optical and near-infrared emission arising from radioactive decay of heavy elements synthesized in the merger, confirming that neutron-star collisions are sites of R-process nucleosynthesis that produce gold, platinum, and other heavy elements found throughout the universe. The coordinated observation campaign collected data across dozens of epochs over weeks following the merger, tracking the evolution of the emission and enabling detailed modelling of the ejector properties and composition. Drawing parallels to 3I-ATLAS, we can envision how a similar coordinated response might unfold if anomalous behaviour is detected. The triggering event, analogous to gravitational wave detection, would be the identification of trajectory deviation, or unusual thermal signatures in astrometric or photometric data. Automated systems would analyse the data to characterise the anomaly, estimate uncertainty, and generate predictions for follow-up observations. Alerts would flow to participating observatories and spacecraft through established channels, potentially including SETI organisations, planetary radar facilities, space agencies, and major optical and infrared telescopes. Within the first 24 to 72 hours, multiple independent observations would either confirm the anomaly and begin revealing its properties, or identify it as instrumental artifact or misinterpretation. The institutional readiness question asks whether such a coordinated response could actually happen, given the current state of organisational relationships and resource allocation. LIGO benefits from decades of planning and investment specifically aimed at enabling gravitational wave astronomy and its multi-messenger extensions. Interstellar object studies lack that focused institutional structure, distributed instead across planetary defence programmes, primarily concerned with impact hazards, small body astronomy focused on solar system populations, and SETI efforts that historically emphasise radio and optical signals rather than trajectory anomalies. Bridging these communities and establishing shared protocols would require high-level coordination, probably involving space agencies and international organisations, along with funding for the necessary software infrastructure and dedicated observing time. Whether tonight's perihelion passage of 3I-ATLAS will trigger such coordination remains to be seen, but the precedent exists in gravitational wave astronomy for how humanity can respond rapidly and effectively when the universe surprises us with something extraordinary. Part 12. JWST reveals more chaotic early galaxies, why cosmic context matters. While LIGO listens to the gravitational symphony of merging black holes and astronomers track interstellar visitors, the James Webb Space Telescope continues revolutionising our understanding of the early universe, revealing galaxies that challenge fundamental assumptions about how cosmic structure forms and evolves. Recent JWST observations from 2025 have shown that galaxies in the first billion years after the Big Bang exhibit more chaotic morphologies and kinematics than theoretical models predicted, with turbulent gas flows, irregular structures, and surprisingly high star formation rates given their young ages. These findings might seem disconnected from the question of whether 3I-ATLAS is a natural comet or an alien probe, but they fundamentally affect the probabilities we assign to each possibility by reshaping our understanding of how common planetary systems are, what conditions favour the emergence of technological civilizations, and therefore how likely it is that engineered artefacts might be drifting through our solar system. The early galaxies observed by JWST appear as they existed when the universe was just a few 100 million to 1 billion years old, a time when the first generation of stars had formed and begun synthesizing heavier elements, but when galaxies had not yet settled into the relatively orderly disk and elliptical structures we see in the nearby universe today. JWST's infrared instruments can observe these distant galaxies because their light has been stretched to longer wavelengths by cosmic expansion during the billions of years it travelled to reach us. What JWST sees challenges the standard picture in which galaxies form hierarchically through mergers of smaller systems that gradually build up mass and structure over cosmic time. Instead, many of these early galaxies show morphologies suggesting violent, rapid processes, bright, clumpy regions of intense star formation, distributed irregularly rather than in organised spiral patterns, evidence for powerful outflows driven by supernovae or active galactic nuclei that expel gas from the galaxies, and kinematic signatures indicating that the gas is moving in complex turbulent patterns rather than in orderly rotation. Some galaxies appear to have formed most of their stars in intense bursts, lasting just tens of millions of years, much faster than models typically predict for that era. The abundance of bright, massive galaxies at these early times exceeds what many models predicted, suggesting either that galaxy formation was more efficient than we thought, or that our understanding of how stars form and evolve in these extreme environments requires revision. Why does this matter for thinking about 3I-ATLAS and the broader question of life and technology in the universe? The connection runs through the chain of reasoning that starts with galaxy formation, proceeds through star and planet formation, continues through the emergence of life and the evolution of intelligence, and culminates in technological civilizations capable of building interstellar probes. Each link in that chain has uncertainties, and updating our estimates for early links propagates through to affect our final probabilities for technological artifacts existing in detectable numbers. More chaotic early galaxy formation means star formation occurred under different conditions than in the present-day universe, with higher gas densities, more turbulence, and potentially different stellar populations dominated by massive stars with short lifetimes. These conditions affect the metallicity of later stellar generations, the heavy element content that determines whether planets can form with substantial rocky cores, and the organic chemistry necessary for life as we know it. If early star formation was more turbulent and violent, perhaps fewer planetary systems formed, or perhaps those that formed experienced more disruption from nearby supernovae and stellar encounters. That would reduce the number of stable environments where life could emerge and evolve over billions of years. Alternatively, the chaos might have accelerated certain processes, bringing heavy elements into the interstellar medium faster than orderly evolution would, enabling second and third generation stars with higher metallicities to form sooner. Those stars could host rocky planets enriched in elements necessary for technological development, like iron for tools and rare earths for electronics. The turbulent environment might have driven more frequent exchange of material between different regions of galaxies, potentially spreading organic molecules or even simple life forms between star systems if panspermia mechanisms operate on galactic scales. The Bayesian framework for evaluating claims about 3I-ATLAS requires prior probabilities for how likely it is that any given interstellar object is engineered rather than natural. Those priors depend on estimates of how many technological civilizations exist in the galaxy, how long they persist, whether they build interstellar probes, and how many such probes might be wandering through space at any given time. Each of these factors traces back ultimately to the conditions under which life and intelligence emerge, which depend on the prevalence and stability of suitable planetary environments, which depends on how stars and galaxies form and evolve. If JWST observations force us to revise our understanding of early galaxy formation toward more chaotic conditions, we must propagate that revision through the entire chain, potentially increasing or decreasing our prior probability for technological artifacts, depending on how the various effects balance. One speculative interpretation suggests that more turbulent galaxy formation might favour the emergence of advanced civilizations by creating diverse, changing environments that drive evolutionary innovation and technological development. Life that emerges in stable, unchanging conditions might have less pressure to develop complex adaptations or intelligence, while life facing variable and challenging environments might evolve more rapid response capabilities and eventually technological solutions to environmental challenges. If true, this would increase the expected number of technological civilizations and therefore increase the prior probability that any given anomalous object might be artificial. A contrary interpretation argues that stable conditions are necessary for complex life to evolve and persist long enough to develop technology. Turbulent environments with frequent disruptions from supernovae, stellar encounters, or galaxy mergers might sterilize planets repeatedly, preventing the accumulation of evolutionary complexity necessary for intelligence. In this view, technological civilizations arise primarily in quieter, more stable regions of galaxies, and in later cosmic epochs, when star formation has settled into more orderly patterns. This interpretation would decrease our prior probability for technological artifacts, especially those originating from very old civilizations that formed during the chaotic early universe. The truth likely lies somewhere between these extremes, with the relationship between environmental conditions and the emergence of intelligence being far more complex than simple, monotonic functions. JWST's revelations about early galaxy chaos remind us that the universe's history includes eras and environments dramatically different from what we observe nearby in space and time. Our theories about life and intelligence rest on very limited data, essentially one example on Earth and 0 confirmed examples elsewhere. Updating those theories as we learn more about cosmic conditions is essential for making informed judgments about the likelihood of encountering other intelligences or their artifacts. The connection to 3I-ATLAS closes the loop. As we wait for data that might reveal whether this particular object shows signs of engineering, we simultaneously must grapple with how much we know, or don't know, about the prevalence of engineering capabilities in the universe. JWST teaches us that the cosmos is stranger and more complex than we expected even a few years ago. That lesson counsels both humility about our ability to predict what's possible and openness to genuine surprises when they appear in the data. Part 13. AI Governance. Flashpoint, a global statement, calling for a ban on superintelligence. Parallel to the search for alien intelligence in the skies, humanity wrestles with the emergence of artificial intelligence on Earth, a development that raises questions remarkably similar to those posed by potential contact with extraterrestrial technology. During late 2025 and into 2026, a coalition of prominent researchers, policymakers, and public intellectuals issued statements calling for international coordination on artificial intelligence governance, some going so far as to advocate for moratoriums or restrictions on the development of superintelligent systems that might exceed human control or understanding. The debate centres on risks and benefits, on questions of who decides what AI systems get built and deployed, and on whether humanity can establish governance frameworks before transformative capabilities emerge that render such frameworks irrelevant or unenforceable. The core concern driving these governance proposals is that advanced AI systems, particularly those approaching or exceeding human-level intelligence across broad domains, might pursue goals misaligned with human values or human survival. Even systems designed with apparently beneficial objectives might, through recursive self-improvement or unexpected optimization strategies, behave in ways that harm humanity while technically achieving their programmed goals. The classic thought experiments involve AI systems optimizing for narrow objectives like manufacturing paperclips or solving mathematical problems, which then convert all available matter and energy toward those goals, including matter and energy humans need for survival. While these scenarios are deliberately extreme, they illustrate the fundamental challenge, ensuring that powerful optimization processes remain aligned with human intentions and values, even as those processes become more capable than we are at achieving their defined objectives. Key signatories to recent governance statements include AI researchers who helped develop current machine learning systems, ethicists and philosophers who study the implications of advanced technology, and former government officials with experience in arms control and international security frameworks. Their proposed restrictions range from modest transparency requirements and safety testing protocols to more dramatic proposals for international treaties limiting certain types of AI research, enforced through verification mechanisms analogous to those used for nuclear weapons or chemical weapons. The political context is fraught because AI capabilities are economically valuable and militarily significant, creating strong incentives for nations and corporations to race ahead rather than coordinate restrictions. This debate matters for the 3I-ATLAS story because it reveals how humanity approaches questions of advanced intelligence, whether artificial or extraterrestrial. If we struggle to govern AI systems we ourselves are building, systems whose training data and architecture we can inspect and whose goals we can at least attempt to specify, how would we approach governing interaction with an intelligence from another star system about which we know almost nothing? The challenges are structurally similar: inferring intentions from observable behaviour, assessing risks without complete information, coordinating responses across institutions and nations with different interests, and maintaining meaningful human agency in the face of potentially superior capabilities. The governance frameworks being proposed for AI might provide templates for protocols regarding extraterrestrial contact. International bodies like the United Nations Office for Outer Space Affairs already have committees that discuss space governance issues, and SETI organisations have drafted principles for responding to detection of extraterrestrial intelligence. These principles emphasise transparency, international consultation before any reply is sent, and caution about assuming benign intentions. If 3I-ATLAS or any future object shows genuine signs of artificial origins, existing AI governance structures and ethics boards might be rapidly adapted to address the new challenge, bringing together expertise in risk assessment, international law, communication theory, and astrobiology. Tensions would emerge immediately between competing values and interests. Scientific openness argues for sharing all data about the detection widely, enabling global participation in analysis and interpretation. National security concerns might favour restricting information that could provide strategic advantages or reveal vulnerabilities. commercial interests in space technology and resources might see opportunities for profit or competitive advantage. Cultural and religious perspectives on humanity's place in the cosmos would shape public reactions and political feasibility of different response options. Navigating these tensions requires institutions with legitimacy across diverse constituencies, clear procedures for decision-making under uncertainty, and mechanisms for accountability that prevent any single actor from unilaterally determining humanity's response. The question of who has legitimacy to respond to contact highlights deep challenges in global governance. No single nation-state represents humanity as a whole, though several possess disproportionate capabilities for space operations and scientific research. International organizations like the UN provide forums for coordination, but lack enforcement powers and often move slowly through bureaucratic processes. Scientific institutions have expertise, but no political mandate to make decisions with global implications. The AI governance debate has highlighted these same tensions, with some arguing that decisions about transformative technology are too important to leave to corporate boardrooms or national governments acting unilaterally, while others contend that international coordination inevitably becomes lowest common denominator compromise that stifles beneficial innovation. Speculative scenarios about repurposing AI governance institutions for extraterrestrial contact management raise intriguing possibilities. Ethics boards currently evaluating AI safety proposals could expand their mandate to include evaluation of protocols for interacting with detected alien artifacts. Safety standards developed for ensuring AI systems remain aligned with human values might inform principles for deciding whether and how to attempt communication with extraterrestrial intelligences. Monitoring systems designed to detect dangerous AI capabilities could be adapted to watch for technosignatures in astronomical data. The expertise being built in one domain could transfer partially to the other, though the differences between artificial and alien intelligence would require substantial adaptation. Perhaps the most important lesson from the AI governance debate is that waiting until transformative capabilities are demonstrated before developing governance frameworks is dangerous and probably futile. By the time an AI system exhibits superintelligent capabilities, it may already be too late to establish effective controls. Similarly, if humanity waits until after detecting clear evidence of alien technology before thinking seriously about response protocols, we will be operating reactively under intense pressure rather than proactively with time for deliberation and consensus building. The fact that 3I-ATLAS may or may not show anomalous behaviour tonight is less important than the reality that eventually, whether through this object or some future detection, we will face these questions for real, and our preparation or lack thereof will determine how well we navigate what could be the most consequential moment in human history. Part 14. Nearby Super-Earth Discovery, Changing Catalogue of Habitable Candidates. The growing catalogue of exoplanets, planets orbiting stars beyond our Sun, has transformed from a curiosity to a comprehensive census that reshapes how we think about planetary systems and the prevalence of potentially habitable worlds. Recent discoveries announced in 2024 and 2025 have added several nearby super-Earths, rocky planets larger than Earth but smaller than Neptune, orbiting within or near their stars' habitable zones, where liquid water could exist on their surfaces. These discoveries matter for contextualizing 3I-ATLAS, because they update our estimates of how many worlds might harbour life, and therefore how many civilizations might exist that could build and launch interstellar probes. One particularly intriguing discovery involves a super-Earth orbiting a red dwarf star approximately 15 light-years from our solar system. Red dwarf stars are the most common type in the galaxy, comprising about 70% of all stars, and their longevity, burning for hundreds of billions or even trillions of years, means they provide stable environments potentially favourable for life's emergence and evolution. The newly characterised planet orbits within its star's habitable zone, receiving roughly the right amount of stellar radiation for liquid water to exist if the planet has an atmosphere. The planet's mass is estimated at approximately 3 times Earth's mass, and its radius suggests a rocky composition rather than a gas envelope. The discovery came through the radial velocity method, detecting tiny wobbles in the star's motion caused by the gravitational tug of orbiting planets. Confirmation and characterization required observations from multiple telescopes over several years to confidently establish the planet's orbital period, mass, and other properties. Follow-up observations using transit photometry, watching for dips in starlight when the planet passes in front of its star from our perspective, provided additional constraints on the planet's size and potentially its atmospheric properties if future James Webb Space Telescope observations can detect absorption features in starlight filtered through the planet's atmosphere during transits. Atmospheric characterization of such planets represents the frontier of exoplanet science, with JWST and future missions like the Habitable Worlds Observatory aiming to detect biosignature gases that might indicate life. Oxygen in combination with methane would be particularly interesting because these gases react with each other and would not persist in an atmosphere unless continuously replenished by biological or geological processes. Detecting such biosignatures would not prove the existence of technological civilizations capable of building interstellar probes, but it would demonstrate that life can emerge on worlds very different from Earth, increasing the plausibility that the universe teems with biology and potentially intelligence. The growing exoplanet census forces us to update our estimates in the Drake equation, the framework for estimating the number of technological civilizations in the galaxy. Each term in the equation represents a factor: the rate of star formation, the fraction of stars with planets, the number of planets per star in habitable zones, the fraction of those planets where life emerges, the fraction of life-bearing planets where intelligence evolves, the fraction of intelligent species that develop technology detectable across interstellar distances, and the longevity of such technological civilizations. Early versions of the Drake equation in the 1960s had to guess at many of these terms because we lacked data. Now we know that most stars have planets, and that rocky planets in habitable zones are common, with perhaps 1 in 5 sun-like stars and a higher fraction of red dwarfs hosting such worlds. The implications for 3I-ATLAS become clear when we work through the numbers. If even a tiny fraction of these billions of potentially habitable worlds in our galaxy develop technological civilizations, and if even a tiny fraction of those civilizations build and launch interstellar probes, the number of artificial objects drifting through the galaxy could be substantial. Most would be inactive relics from civilizations long extinct, but some fraction might still function. The interstellar visitor rate observed at Earth, approximately 1 object per year based on extrapolations from Oumuamua and Borisov detections, provides another data point. If most interstellar visitors are natural debris from planetary systems, and only a small fraction are artificial, even that small fraction translates to potentially 1 artificial object per decade or century passing close enough to detect. These probabilistic arguments don't prove that 3I-ATLAS is artificial, but they establish that artificial interstellar objects are plausible in a way they weren't before we knew about exoplanet ubiquity. The burden of proof remains high, requiring clear observational evidence rather than statistical arguments, but the prior probability has shifted from essentially 0 to small but non-negligible. That shift matters for how we interpret ambiguous data, how much resources we invest in follow-up observations, and how seriously we take proposals for missions to intercept and study interstellar visitors. Speculative connections between specific exoplanets and 3I-ATLAS invite imaginative storytelling, but rest on minimal evidence. Could the object have originated from the planetary system around that nearby red dwarf? The trajectory doesn't point back toward that star system, but gravitational interactions during its journey through the galaxy could have altered its path substantially, erasing any clear connection to its origin point. Could a civilization around such a star have been launching probes for millions of years, seeding the galaxy with observers? That scenario requires assuming capabilities and motivations we have no way to verify, but it fits within the boundaries of what physics allows, even if it remains wildly speculative. The distance and travel time constraints provide sobering context. If an object was launched from 15 light-years away and travelled at 30 kilometers per second, typical of interstellar visitor velocities, the journey would take approximately 150,000 years. Any civilization that launched it would have changed or possibly disappeared during that time, meaning the probe operates independently of its creators, following programmed instructions or autonomous decision-making algorithms set in an era incomprehensibly distant from our own. Communication with the origin civilization would be impractical given light speed limits, with any message taking 15 years to arrive and another 15 for a reply, and that assumes the civilization still exists and monitors for signals. These discoveries and the questions they raise transform the search for extraterrestrial intelligence from speculation to a data-driven scientific program. We now know the targets exist, the potentially habitable worlds where life and intelligence might arise. We know the physics allows for interstellar travel, though at speeds and timescales that strain comprehension. What remains uncertain is whether life emerges commonly or rarely, whether intelligence evolves frequently or represents a unique accident, and whether technological civilizations typically develop interstellar capabilities or destroy themselves first. 3I-ATLAS, whether natural or artificial, provides one more data point in this grand investigation. Part 15, AI and Space Tech in October 2025. Infrastructure and capability upgrades. Something is changing quietly behind the scenes of science. It is not an alien probe or a mysterious object streaking through the void, it is us, or rather, the new intelligence we have built to look at the sky on our behalf. Tonight, as telescopes search for any flicker of movement from 3I-ATLAS, a second revolution is underway in the servers and observatories of Earth. Artificial intelligence is now watching the heavens faster, more precisely, and with less human hesitation than ever before. If this object makes a move, it will not be an astronomer who notices first. It will be an algorithm. Over the past months of 2025, every major space agency has quietly integrated new AI-driven systems into their data analysis pipelines. NASA's Frontier Data Lab released an upgraded anomaly detection suite that can scan petabytes of sensor data in real time, filtering out noise from solar flares, cosmic rays, and instrument errors to leave only the signals that truly don't belong. The European Space Agency followed suit with an automated rapid targeting platform for deep space events, software that can schedule telescope time and re-aim instruments autonomously within seconds of detecting a deviation. The result is a global network of digital sentinels faster than any command chain, always awake. This new infrastructure means the world no longer waits for human interpretation. When a sensor blinks, when a photon arrives a few milliseconds late, when a comet brightens a little too early, AI sees it first. For objects like 3I-ATLAS, this is revolutionary. In earlier decades, we lost critical data simply because no one was watching at the right moment. Now, even when the object slips behind the sun, systems like NASA's Heliophysics AI Monitor and the Japanese Hinode AI pipeline continue running models that predict what we can't see, estimating thermal fluxes, possible thrust signatures, and orbital perturbations. We are teaching machines to imagine what's hidden, but these tools do more than predict. They learn. When Atlas was first tracked, neural networks began comparing its light curve against millions of known comet profiles. Within minutes, they flagged it as non-conforming. That kind of alert once required days of human cross-checking. Now, it's instant. If tonight's perihelion shows any energy anomaly, a flash of excess brightness, an unpredicted deviation, AI systems from multiple observatories will correlate those changes across wavelengths and automatically propose explanations. Fragmentation, outgassing, propulsion. The moment of discovery will arrive in the time it takes you to blink. Of course, the same speed that empowers discovery also multiplies confusion. In October alone, several fake AI-generated telescope captures of 3I-ATLAS went viral within hours of being posted. They looked real, lens flare, exposure patterns, even simulated CCD noise, but they were entirely fabricated. Generative video models have reached the point where a convincing alien probe maneuver clip can be created on a home computer in an evening. Misinformation now evolves as fast as real science. The same neural architectures that reveal the universe also forge illusions of it. Institutions are scrambling to adapt. NASA and the European Southern Observatory recently launched authenticity frameworks for astronomical imagery. Each image from an official telescope now includes an encrypted signature, a kind of digital DNA verifying its origin. Independent researchers can trace a frame back to its source, ensuring that what they see was truly captured by a sensor, not conjured by code. It's a start, but the battle is uneven. For every verified data stream, 1,000 synthetic ones circulate in social feeds, blurring truth and speculation. The problem is no longer lack of data, it's too much of it, too fast. Still, there is wonder in this transformation. AI is not only filtering and flagging, it is beginning to hypothesize. Models trained on decades of astrophysical data are now capable of proposing new orbital fits and energy models that humans might overlook. Some researchers call this the birth of synthetic astronomy, a fusion of observation and machine intuition. In one experiment this month, an AI-assisted scheduler re-aimed a small telescope array in Chile toward a region of sky it predicted would show increased activity from interstellar debris. Hours later, a faint moving object was indeed detected, likely unrelated to ATLAS, but statistically improbable without the algorithm's guidance. The universe seems to reward curiosity, no matter who asks the question. And yet, the moral questions linger. Who decides which anomaly deserves attention? Who confirms what the AI reports? In a future where machines analyze and interpret cosmic events faster than humans can comprehend, how do we maintain the line between discovery and interpretation? The story of 3I-ATLAS may one day be remembered less as the day we found alien technology, and more as the day we realized our tools had surpassed us as explorers. The technological arms race in the sky doesn't stop at observation. Mission planning assistants powered by large language AI models are now helping scientists simulate orbital encounters, fuel expenditures, and data relay schedules in minutes instead of weeks. NASA's mission design AI, codenamed Kepler-2, recently generated optimized flight plans for over 50 hypothetical interception missions to interstellar objects. These are not fantasy. They are draft-ready blueprints. Should a true alien probe ever pass by, humanity could theoretically launch a response craft within months, not decades. We are quietly preparing for first contact, whether we admit it or not. But as our tools grow sharper, our perception grows more fragile. Every advance in AI-driven astronomy amplifies the potential for human bias to creep in unnoticed. If a model expects to see an engineered maneuver, it might find one where none exists. The algorithms don't dream, but the people training them do. And so, even as we push toward automated cosmic vigilance, we must keep one human trait at the center: doubt. Healthy, scientific doubt. The humility to ask whether we're seeing the universe as it is, or as we've taught our machines to see it. If 3I-ATLAS turns out to be nothing more than a natural comet, that outcome will still be historic. It will mark the first time our global AI infrastructure performed a coordinated, high-speed observation of an interstellar visitor. Billions of lines of code working in unison, passing terabytes of data, all to answer one ancient question. Are we alone? Maybe not yet, but we're finally ready to notice if we aren't. So as the world sleeps, the servers hum, the observatories pivot, and the models run in silence. Somewhere between the photons and the predictions, a truth is waiting to be found. Whether Atlas did something tonight or not, the real story is our readiness, or lack thereof, to see and react when the universe surprises us. Maybe nothing happened at all, or maybe something did and we just haven't realized it yet. Either way, I'll be watching the data feed. In the coming weeks, I may update you live as we learn whether this moment changed everything, or reminded us how close we already are to the edge of understanding.